Anyway, so this is what I'm really going to be talking about. It doesn't sound quite so attractive, but it is absolutely fundamental, of course, to what most of you guys are doing here, which is trying to understand the real geological signals that have been recorded by rocks over many millions and billions of years. So I've got a couple of applications that I've just put in this initial introduction. One here is this image, which I've stolen from MIT, which of course shows these conglomerates or aggregation of mass in the protoplasmic disk that was the forerunner to the development of the Earth and other planetary bodies. And here, of course, what they're trying to do is to try and understand what the variation in the magnetic field across this disk was, because there's still this painful problem of trying to distribute angular momentum out of the planets and mass into the sun, which isn't completely solved by classical theory. So understanding the magnetic field recorded by these meteors, and asteroids through the protoplasmic disk tells us about whether the field can interact with the mass to try and distribute the angular momentum. Because closer to what you guys are doing is something like this. This is by Alec Brenner and Roger Fu, which have shown, I think these samples probably, Andy, you remember more than I do, from Western Australia, I think, where they estimate from these samples of 3.35 billion years old that by that time there was a strong dipole field, active late tectonics, and so certainly Alec and Roger favor that over the alternative at that time. I think was being proposed, this silicate dynamo in the mantle. So all of these really ancient stories that are held within magnetic material, they consist really of the only record we have of events at the time that these processes were changing. And so this isn't secondhand, these are actual recordings of physical processes that are going on millions, thousands of millions of years ago. Oh, this is a list here of all the different, I normally rearrange this depending on where I'm visiting. I should have put Les, Greg, and Brendan, because they're first up on the list. I obviously put them wrong. The wrong one. Okay, so the key point really, as far as we're concerned, is going and collecting the samples, measuring them, and if we want to get the paleointensities, then we look at the replacing the samples magnetization with laboratory magnetization, and we hope we get nice straight lines, as Greg always does from his samples, as we can see here. Unfortunately, we all know that isn't normally the case. We have 80–90% sample failure, a lot of money used, even if there's going to sunny places. Obviously not so sunny here. Is this one of your pictures? Okay. Yeah. Where was that?
St. Helena.
Okay. Well, yeah, not so nice on that day. Okay, but the problem is that you collect those samples, and it's really difficult to predict in advance which samples are going to produce a really good recording, or which have recorded accurately the ancient field, and which do not. So this is more typical, I think, also from Greg. And you get a huge amount of scatter. I think we're all familiar with these. And this is just a random image I've taken from Isotopsis' paper, showing that the range of various estimates we have as a function of time in the past. So a lot of scatter. It's hard really to determine anything absolutely. Of course, we're not the only science that struggles with being able to be highly accurate in our predictions, but it is a problem. And I'm sure you'll be familiar with these graphs. Again, just to demonstrate that even really pressing problems, really fundamental to the evolution, which people here been trying to determine for a long time is the age of the inner core nucleation. Of course, we don't just rely on paleomagnetic evidence for this. We look at thermal studies of the Earth. Thermal studies, of course, are in a worse state than us because we don't know exactly what's in the outer core. We don't know the elements there. We don't really know the thermal conductivity. So actually, paleomagnetism is probably the best way. This is the direct measurement of what we might expect from a change in the energy of the inner core and how it might be expressed in terms of the paleointensity. So, but even so, you know, over relatively recent years, we have different estimates. So this is yours, Andy, and other people have suggested that it isn't quite so old. And then Claire Nichols was doing a tour of the UK and giving a presentation. She's saying, actually, no, she thinks it's much older than 500. So, you know, I think there's still a huge debate on these really fundamental things that tell us how the Earth was formed. Of course, I'm not going to tell you anything so grand today. I'm really just looking at the mechanisms by which we can decide whether our paleomagnetic recordings are reliable. The hope is that we better understand the recordings that we measure in the lab, or at least, really, we like a method of being able to pre-select our samples or have some other independent means by which we can know how reliable the recordings in our rocks are. Hopefully you're all familiar with this. This is the wonderful day plot. It could be without a day plot. And our traditional view of the reliability or stability of paleomagnetic recordings is in a particular mineral as the grain size increases. So, you know, the traditional view of the day plot is that everything plots in this PSD range, because at the time that they generated this analysis, nobody really knew what the pseudo-single-domain grains are. I think we're getting a better handle on that. And everything was interpreted in terms of the characteristics of these stable single domains. So even PSD grains were somehow deemed to have inherited some single domain-like attributes. And really that's as much as we knew for many years. So for magnetite, though, if we look at the, as we know now, what the range is, at least for equidimensional magnetite, below 40 nanometers is all super paramagnetic. Above 80 nanometers, it's no longer single domain. Of course, that's just for equidimensional, and the range will vary for elongated grains. But actually, for the grain sizes that you have any samples, it's a tiny, tiny fraction. Hardly any of your samples are going to be perfectly uniformly magnetized. Even single domains vary from the classical stability that you might predict from the L theory because of the deformation and the slight variations in the magnetic structure within them. This is one of my favorite papers. I really like this just because of the title. Hunting of the Sark, a paper by David Dunlop, who was trying to, in 1977, was it 77, 76, trying to understand what these pseudo-single-domain grains were, what the structure was, and particularly how stable they were. And the title of this paper, Hunting of the Snark, is to do with Lewis Carroll's poem that talks about this strange creature that everybody was hunting, but nobody really knew what it was. And for many years, that was the case. We were always measuring magnetic signals recorded in these pseudo-single-domain grains, but nobody really understood their stability. Certainly nobody knew what the structure was. With hindsight, it might be perfectly obvious what else was it going to be, but you know, at that time it wasn't. And then David's own view, or he looked at various different structures. One of them was a sort of another attempt to fit in a multidomain grain into very small particles. So you don't have multidomains, well, you have multidomains, but you have rather few of them. So these are two domains with a domain wall, where the remanence resides within the domain wall. Actually, 30 more years ago when I started out, this was the kind of model, even micromagnetics, that we were looking at, is to have a one-dimensional micromagnetic model where we twisted the magnetization. If you twist the magnetization, all you're left with is a remanence in the middle, that resides in what looks like a domain wall. But the problem with all models is that if you constrain them enough, they tell you something that isn't true. This isn't true. So between 35 years ago and now, we've built these micromagnetic models. I've been doing them for a long time. A big boost came when Les was a PhD student of mine a long time ago. And this is now public software, of course, and I think it has some utility to it, in that you can go and look at magnetic structures, and they will tell you they're reliable, how reliable they are for different minerals, different types of grain morphologies. However, this is another one of my favorite slides, that it's still a model. Any model is an approximation of the truth. And this famous quote by George Box, who was an accountant or statistician, probably both. He said all models are wrong, but some are useful, and that's absolutely true. So we don't attempt to model every possible feature of a mineral. We attempt to use it to describe a general behavior of a system. So we don't expect that in any particular instance, what we predict in any particular grain is absolutely accurate to the magnetization on each atom. There are programs that attempt to do that, but we don't attempt to do that. But we do attempt to build up a general theory of stability as a function of mineralogy and grain morphology. I'm going to do this. I have a terrible habit of rattling on. You should ask my undergraduate students when I get through about half the course material that I'm supposed to every year. So I try to keep it some time. I'm going to run through just a few slides that show the variation of magnetic structure as a function of grain size. This is actually work of Les here, who built this really fabulous, completely independent micromagnetic model as a PhD student. And these are the results. This particular micromagnetic code was good for very large models, going up to about 3 million elements or something more. But what it allowed us to do is to trace the development of domain structure as a function of grain size right up to multi-domain grains. So these pseudo-single-domain grains, of course, completely obvious to me now because I've looked at them too long, but they are vortex structures. So pseudo-single-domain grains, or I should say vortex structures, are an example of a pseudo-single-domain grain. It isn't exclusive with any other types of structures. And of course, in very high anisotropy materials, you probably wouldn't get vortex structures. But in magnetite, for sure, Titan magnetites, these vortex structures dominate the pseudo-single-domain grain size range. And the grain size range, as we'll see shortly, is at least an order of magnitude larger than the single-domain grain. They have larger remanences because they're larger grains. So the chances are, in any paleomagnetic sample you have, these type of structures are a dominant or a significant contribution to the remanences that you're measuring. So if we look at, this is just how I'm visualizing it, or Les visualized it. So this is the magnetic structure with the magnetization represented by vectors on each node of a finite element. We do a nice surface to illustrate the core of the vortex and its orientation. And these are contour surfaces of anisotropy, where blue is easy aligned and red is hard aligned. So it just shows you how the magnetization likes to align along a preferred crystallographic axis. But it has to move out of those easy directions in order to form different domain structures. So this is a 200 nanometer grain, already well-defined domain structure. And as we go up in grain size, you can see the development of these more linear structures at the outside of the vortex core. That, as I'm going to go through this really quickly because it's not essential to the thread of the talk. But as you go up to 1.5 microns, 2 microns, and 3 microns, oops, not 3 microns, 2.7 microns, which we would say is at the boundary of the transition in a roughly equidimensional grain transition between what we normally think of a PSD grain and a multi-domain grain. Why do we say that? Is that if you see these light blue structures here, these are domain walls. We can measure the width of those domain walls. We can compare them to an analytic solution, what we might get in infinite domains, and they turn out to be the same width. So we think at about 3 microns is a reasonable transition from these simple vortex structures to multi-domain structures. There are all sorts of other structures that you may nucleate as well, but as a simple transition, we would say about 3 microns is where you get these more complicated multi-domain structures, which, of course, we know traditionally, at least, accept are less stable, less reliable paleomagnetic recorders because the domain walls are more mobile and don't hold the remnants over many billions of years. So this is the summary of those, and this is an example here of the range, both in grain size and elongation, of the region which we find single-domain grains and the region which we find single vortex grains and the region which we find single-domain grains. So these single domains are really a tiny fraction of what we're likely to find in grains, in samples which have a reasonable, a normal type of distribution. It's only really the very, very fine, fast-cooled materials that you might be dominated by single domains. So, of course, we don't have to look at idealized grains. One of the things that I'm doing in much with the Imperial and with Greg in Liverpool is looking at more complex structures that can exist in more realistic structures, and this is a range of grains that were found in some samples from Vesuvius, and so you can see a huge variety of different grains, and you can might imagine that these have a wide variety of different domain structures and stabilities and so forth, but actually you do the micromagnetics, and they're still dominated by these vortex structures, and may be interacting, but all these things are dominated by the mobility of these vortex cores, and these are predictable and allow us to get a reasonably accurate estimate of the reliability and how they react to thermal cycling, which you have to do your paleointensity experiments. One of the things I should point out is that these numerical models that we produce are not done in a vacuum, so to speak, in terms of trying to predict the magnetic properties of materials. We try to validate them, and this is an example of a grain that we looked at, or some electroneurography, sorry, of a magnetic particle. This is a magnetite particle that we looked at under electroneurography back in 2018 with Trevor Almeida, who was a postdoc at that time, and is now in Glasgow University. So this is the grain that we looked at, and this is the electroneurography that showed it to be, well, if you looked at that, you might say it's a multi-vortex, 2 vortex cores, but actually it's a single vortex. This is the numerical model that we predict from using the exact morphology of the grain. And this is then our prediction of the electroneurography result that we should get. You can see it's a pretty good match. I would say that's a pretty good match. So that's a single vortex. You might say single vortexes are easy to predict. How many ways can we fit a single vortex into a particle? But we can do more complicated stuff. This is using magnetic force microscopy, which is basically you drag a needle on top of a sample and you measure a stray field peeking out of the surface. This was done with some people from the Rock Mag Institute in Minnesota, and this was a 1.4 micron size grain of TM54, which has quite a complex magnetic domain structure. So this is our model of what it should contain. As we can see, these models in the top row here. This is the simulation of the MFM surface observation that we think you should observe from this grain, and below it is the experimental observations. So even quite complex structures, multi-vortex or significantly more complex than a single vortex aligned with the grain axis, we can see good agreement between experimental observations and theoretical predictions. So we're reasonably confident, as confident as we can do, that our models are telling us something useful, as Professor Fox might say. What we're really interested in, of course, is the stability and the thermal stability, because what you do in order to determine the paleointensity is heat them up and cool them down, heat them up and cool them down, replacing in a stepwise fashion the remnants that they contain. And so probably you're already aware of this concept of magnetic blocking, where at high temperature, the relaxation time or the direction of the magnetization can easily align with an external field, and at low temperatures, it becomes blocked and becomes virtually impossible to rotate that magnetization even over long time periods. So that's these particles that can hold magnetic recordings for many hundreds and thousands of millions of years. So this is a concept of blocking, and it depends upon the energy barrier, which is temperature dependent, the energy barrier between rotation of the magnetization, or different magnetization states that are possible in the grain. If you can determine the energy barrier between them, then you can determine the relaxation time at any temperature, and you're looking for the relaxation time as you cool the temperature that falls to about your observation time, maybe a few seconds or a few minutes. But this is a very sharp process. So we tend to think of the blocking as almost instantaneous in terms of temperature. For single-domain grains, this is a very simple equation. You can determine the blocking temperatures as a function of grain size here and axial width. I've done this calculation up to 80 nanometers. Of course, we wouldn't think that beyond 80 nanometers was a single-domain anymore, but anyway, we could predict them. And the blocking temperatures are shown here as these contours. Of course, we've been able to calculate these blocking temperatures for single domains since 1954, or whatever it was, and Yale came up with this single domain theory. We'd like to be able to do that for these non-homogeneously magnetized particles. Before I go and show you some of those types of calculations, an absolutely vital part of your paleomagnetic experiments is this principle of reciprocity, of blocking and unblocking. If you haven't got reciprocity in blocking and unblocking, then you might as well just throw your samples in the bin. Because what you depend upon when you remagnetize the sample and demagnetizing it, you're assuming at every point that you are remagnetizing at the same temperature those particles that were originally magnetized in the field. And this must be repeatable. So this concept of blocking, as you cool the sample down, as you pass the blocking point, the energy barrier becomes so large, the thermal fluctuations no longer are able to change the direction of magnetization. When you heat it up, you expect that same particle to unblock at exactly the same temperature as it was blocked. All being well, you can obtain a remanence, which you can demagnetize at various temperatures. You can remagnetize it at those same temperature intervals. You plot the ratio, they're all plotted in a nice straight line, and everybody's very happy. Unfortunately, this lack of reciprocity hardly ever holds true. Hardly ever. And that's been known for a long time. This is a paper from David Dunlop in 2010, where he did this really, really simple experiment on pure magnetite. Probably was interactive, but nevertheless, it was pure magnetite of precise grain sizes. Well, as precise as you could get them. And he put in a magnetic remnants that was blocked between 350 and I think it's 25, oh, 350 and 370, in 20 degrees. So he's cooling it down, turn the field on at 370, turn the field off at 350, and cool down again. So in principle, if you heat those up, everything should remain blocked until 350, and then unblock completely after 370 degrees. And as you can see here, for these different lines, for different particles sizes, so 0.6, still quite large, but none of them obey this principle of reciprocity. In fact, many of them, I would say for most of them, over 90% of that remanence unblocks either before or after the blocking temperature. All this part here is going to contaminate your paleomagnetic intensity, and this is what. If it doesn't unblock and unblock at the same temperature, then you're in trouble. And this is what you get. Rather than get nice straight lines for the PTRM that you replace, compared with the remnants that you're demagnetizing, you get these curvatures, these curved Y plots. And Lisa Torps wrote a very nice, somewhat complex paper about fragile curvature, where she talked about this curvature changing depending upon the storage time of your sample. So something was happening to those domain states that somehow made their behavior different. I think we have the answer to that. So if we wanted to calculate what the energy barriers are, we can't do it analytically. We have to do it using micromagnetics for these non-uniformly magnetized particles. This is a standard method we use many years now called the nudge-elastic band method. And we simply find the minimum energy path between one orientation of the magnetization and another. So we search the phase space, if you like, of magnetic solutions to find minimum energy structures, and then we look for the minimum energy path between one domain structure and another. And that's all we need to get this energy barrier, and then we can get the relaxation time. Assuming this, it's not going to, okay. So this is what we found, a very, in my mind, amazing paper by Les and others that shows the stability of grains as a function of grain size. This is just for equidimensional grains, but it was the first one that demonstrated absolutely conclusively that, well, it demonstrated two things. First of all, for vortex structures, they are incredibly stable. That's great news, right? So despite the fact that none of your samples are single domain, upon which your interpretation was implicitly assumed, they're still pretty good. Right? In fact, they're much more stable than single domains, as shown by this blue line. And the other thing they showed is that the stability of the single domains is not exactly as classical theory would predict either. There's a bit of, even in single domains, there's a bit of deformation of the structure. They form as flower states where the magnetization tends to bow out towards the near surface of the grain. And that changes the stability, so they're slightly more stable in certain geometries than Leo would have predicted. Okay, so that's all good news, but it's only good news if our vortex particles obey this reciprocity that's needed in all paleointensities. So we can look at that also, and this is a paper again that Les published. Yeah, sometime I should present my own work as well. This is much more fun. This is work I did with the guys. And Greg, in fact, some time ago, where we look at the magnetization or the minimum energy states that can be nucleated in a particular grain size. And we just take an example here, a 100 nanometer cubo-octahedral magnetite, 30% elongated. It sounds rather esoteric. It's just an example. Most grains, I would say, you can argue about most data, but most grains will show this effect to some degree or another. The question is, to what extent, but that's something we're also working on at the present time. So the first thing we do is to look at the various domain states that can be nucleated. And the domain states that can be nucleated in this particular grain are vortex states that are aligned along different axes, aligned along the elongation axis, which is this one here, and then also along the short axis. It may not appear short, but it is. and also there's another one along the 90-degree axis to this. So there are 3 different domain states. And the major issue in terms of paleointensities are that those different orientations, which have different magnetic strengths, and because if a vortex is magnetizing along the long axis, it's going to have a larger remanence compared to when it's magnetizing on the short axis of the grain. And which domain state is favored depends upon its temperature. So if you increase the temperature of this grain, it would, at low temperature, favor the short axis. Is that right? Short axis, yes, and then as you get above 164, it favors the long axis. So that then can cause problems if you are continually thermally cycling your sample. It can change between these long axis and short axis. And this is how it changes. So this is a phase map, which can look rather complicated, but it isn't really. It's showing the transition, the favored transition between the different allowed domain states. So we have this red curve that shows the relaxation time between the magnetization that's aligned along the short axis going towards the long axis. The green line here shows transitions between 2 short axis magnetizations, and this blue line shows a transition from a domain state that's along the long axis and transitioning to one of the short axes. And you can see that the favored state also depends upon the cooling rate. So the cooling rate is indicated by these black lines here that are marked at a particular relaxation time. If I get a better example of this, let me see. Well, not really. Okay, but if we take let's have a look. If we take a very slow cooling rate, then we can see that as it cools from high temperature, the first domain state that's going to be locked in is the short to the long aligned. So that means that that the short axis magnetization is going to be preferred at long cooling times, because that's what locks in first. At very high or rapid cooling rates, then we get a magnetization along the short axis. Did I say that the wrong way around? Anyway, you get a magnetization that first locks in along the long axis. I'm sorry, so that it is no longer able to transfer to a short axis. So at fast cooling rates, the long axis is preferred. So this not only then tells us that different domain states are available or preferred at different temperatures, but it also states that you can get different populations of domain states depending upon the cooling rate. Oh, okay, so that's what I said. I think hopefully the fast cooling favors the long axis and the slow cooling favors the short axis. So this is a useful reminder then of what's different between our standard single domain theory, upon which paleointensities are normally founded, and what we get in single vortex theory, what's possible in single vortex theory. So single domain theory says that the blocking and unblocking always occurs at the same temperature, so that this reciprocity of blocking always holds. That is because one favored domain state occurs at all temperatures. You only have single domain, right? So that single domain state is the only domain state that's available to it, and the magnetization strength is independent of orientation. So the magnetization can rotate within that grain, and the magnetization is basically saturation magnetization times the volume of the grain, so it never changes. In single vortex theory, as we've just seen, the blocking temperature and unblocking temperature need not be the same, and it has different choices of domain states that can be favored. And that domain state is dependent upon temperature, and it's dependent upon, in fact, its whole thermal history, its thermomagnetic history, because you can get a population of grains, you can heat it up to a certain temperature and cool it down and heat it up again, and each time you're taking a percentage of those into a different domain state according to this phase diagram. So as you cycle up and down, it depends upon which boundaries in these curves you hit, and above what cooling rate will tell you the fraction of those grains that move into any other domain state. The biggest effect we see is in these elongated grains where the magnetization is no longer independent of orientation. So the orientation depends upon the direction which the magnetization is placed. So the long axis has a high remanence, the short axis, short remanence is completely different to the single domains. And so as we move the populations between these different orientations, according to this phase diagram, then we get different magnetizations. You can possibly cool it up, have a sample that is aligned mostly, say, along the short axis. So there's a low remanence, you can heat it up, and say heat up quite rapidly in the lab and cool it down. Now that favors the long axis, and you can end up with a sample that's more strongly magnetized. Even if you magnetize in the same field as the original field, it'll be much more strongly magnetized than your original remnants. That's nothing to do with chemical remnants, nothing to do with incorrect field settings. It's simply to do with the fundamental nature of the alignment of magnetization in these inhomogeneously magnetized grains. Excuse me. So this is the math, which I'm not going to dwell on. But this simply says that when we do these calculations, and I'm going to show you some simulated Y plots, simulated paleointensity curves shortly, we look at every possible transition from one orientation to the other. So this is mimicking a sample that consists of entirely this one type of grain. So it's the worst possible situation you can imagine, really, if you're trying to look at the paleointensities, because you know this grain has a lot of different domain choices, which switch in the middle of its temperature range between room temperature and the curing point. But for a population of grains that consist of this type of grain size and shape, these are the various domain states, and each temperature we calculate the transition rate between one state and any other possible state. And it's just looking at the movement of the population of domains in any particular orientation. So we can put in any thermal cycling you want. I wouldn't say trivial process, but it's this is a model. We can put in any thermal history you want. We can imagine any original thermal process that recorded the original NRM, and any subsequent thermal treatment we might do to that sample in the laboratory, or any other thermal event that it may have had in its past. So this is a simple Telia type paleointensity experiment. In our models, we also put in, how many of you are paleomagnetists, are you? Oh no, okay, right, I'm sorry. Okay, so we built into our simulations standard paleomagnetic tests. These are called, what are called PTRM tests and PTRM tails. I don't really want to explain what they are, except they're supposed to indicate whether the remagnetization has happened correctly, essentially, that nothing untoward in the sample has happened. And where you do find errors or inconsistencies that are highlighted by these PTRM tests or PTRM tails, well, Andy, what would you normally say causes those?
PTRM, well, yeah, you get alteration, but yeah, you kind of know that it's not just alteration.
Yeah, okay, so I was going to say this is the classic example. Everybody says it's alteration. So obviously what I'm going to show you here is not due to chemical alteration. So this is a simulation of a sample which we said was originally cooled over 6 times 10 to the 8 seconds. Somebody can do a quick calculation of that in years. It's a few thousand years, I think. And then a laboratory cooling rate of just a few thousand seconds. So it's an hour or so. And we get something that's not a very nice Orion plot. All right, we get these crazy variations. However, there are indications, I think, that some things are not right. So these are our PTRM checks. So these PTRM checks, if it was correct, this curve would point to 150. So it's basically remagnetizing it to 150, and it's not where it should be. We've got another one here at 250, which is not so bad. Then we've got a PTRM tail check, which is basically demagnetizing things twice to see if we can get rid of any magnetization we've put in there. So this is really a test of reciprocity. We put in the magnetization in the laboratory and we're trying to take it out. We should be able to take it all out. If we took it all out, the PTRM tail test would be 0, but clearly it's not. It's massive. And so this is our demagnetization of the original NRM. This is our PTRM that we placed in the laboratory. You can see this is done. Okay, so the lab field is twice the. Oh, sorry. The lab field we used was actually the same as the ancient field, but this is the prediction. Right? We predict here from what nobody would attempt to well, some people might attempt to put a straight line through that, but most people would realize it's not a reasonable thing to do. And we predict that the lab field, we predict the ancient field is 15 microtesla's, where in fact it was 30 microtesla's. The remagnetization, even in the same field in the laboratory, has produced a much larger remnants. And I probably don't want to go through, what time did I start? How long have I got left? Sorry, is the okay, so I'm not going to explain too much of the theory. So one of the things here that we can see are these hooks at the end of the Orion plots. These are not uncommon, and that is an indication of a movement of domain states, and the domain states are no longer the same. And that's an explanation of why I don't really want to go through. The issues that we see in these plots are, in fact, associated with cooling rates, because we are placing magnetization in a different cooling rate than the original one that shifts the population of domain states from one type of domain to another. If we do it in the same field, and I'm not sure if I put this in, no, I didn't. If you do it in the same fields, in the same cooling rates, then it's not so bad. And I think this one isn't shown here, but this is in the same cooling rate as the NRM is placed in the same cooling rate roughly as the lab field, and we get a region at least where the magnetization behaves reasonably well. Okay, to the conclusions. I'm sorry for taking so long. The main takeaways, really, what I'm trying to tell you, the most important parts, is that these vortex domain states probably do dominate most of your paleomagnetic samples, and they are very stable, more stable in fact than single domain grains. This is great news for paleomagnetism, great news for planetary science as well, that we have the possibility, in principle anyway, of being able to record these events that are billions of years old. The problem is that sometimes in some types of grains that the replaying of this magnetization causes problems because of the difference in cooling rates and because of the difference in the availability of domain states at different temperatures. That is something that affects certain vortex states. It doesn't affect them all, otherwise none of your paleomagnetic samples will ever work. The question is which ones of them are likely to be more affected than the others, and probably Greg and Les has a good idea of why. I think I do too. Part of the problem is cooling rates, exacerbated by the fact that cooling rates select different populations of grains, which then have different magnetic strengths. It's all to do with this failure of reciprocity. So your erratic plots that you have in your samples may not always be attributed to chemical alteration. If they're not due to chemical alteration, there's a possibility of extracting some data from these, I think, but we're not there yet. One of the strongest indications, I think, of things going awry is these PTRM tail checks. These, rather than PTRM checks, and probably detail here that PTRMs, you can fake and fake. You can have samples that behave, but rather nevertheless give a negative PTRM check. PTRM tails are much more difficult to overcome. So PTRM tails, I think, are a good indication that something is not right in the magnetic domain states. So that's already what I've said, that our vortex structures, we've stuck with them. That's what we have in our samples. There's no good saying that they don't exist because they're there. It's how then we can best interpret the data that we get from them. And the remaining question is to look at different mineralogies and to look at different types of morphologies, probably, that are better behaved than others, or at least to look at what temperature ranges in certain types of grains give reliable signals compared to other grain sizes. Okay, I think that is the end. Sorry, it was a rather rapid gallop through there. Still awake, Richard?
Are there any questions?
I am definitely still awake. I have a question, but I'll let other people go first.
You can go first, Richard, if you want.
Okay, I'm going to ask my slightly mean question, which I think I might have asked a little bit in this form before. So in the introduction, you trailed us the excitement of being able to decide which measurements are good and which measurements aren't, and somehow improve the measurements so we get a better understanding of the field. Yeah. Now, at the end, I got the idea that it has to pass the PTRM check, which on the whole, people kind of say that it should. I've been listening to these talks for, what, 30 years, I think, from on you doing this. And I keep on hoping that you're going to...
Oh, okay.
He's still there.
Yes.
Okay, I can anticipate maybe what he's going to say. So indeed, well, I think we've come a long way in 30 years, first of all. So I don't think I was doing these 30 years ago. And so I think, I hope he was going to ask, how are we going to give you a way of reliably assessing the fidelity of the paleomagnetic signals that you observe? And I think what we are seeing are that these multiplicity of states that vary, their preference for domain states varying at different temperatures, probably is restricted to domain states where there is a balance, a very fine balance between the energies of the different domain states. So if I had a much larger grain, for instance, that was elongated, or, well, it does not have to be elongated, there'd probably be a preference for the magnetization, say, along the vortex, along the grain axes. And there may be other domain states that you can nucleate in that grain size, but one domain state would always be dominant. So over a large temperature range, say from, well, hopefully from room temperature to the Curie temperature, one domain state would be dominant. So you may be able to nucleate those other domain states, a small fraction of them, but there'd be one dominant state. In the case that I've shown here, it was one of the worst cases where there's a very fine difference in the energy between these different domain states. So in another piece of work that's done by a colleague from China, he's looked at a much larger range of domain states in iron. And for sort of a log normal distribution, I can't remember the actual mean grain size or the width actually, but I think he took some grain size population he found from some lunar rocks or something, and he estimated that about 10% of the particles were affected by this multiplicity of domain states. So it may be that, for instance, you might want to pre-select your samples to have mostly elongated grains, or to be away from slightly away from equidimensional grains, for instance. There are possibilities, and also many grains do show this effect, but restricted to a certain temperature interval. So this preference, a change in preference for a domain state, occurs if it occurs at 550 degrees, then it's not such a big deal, right? Because you've got your whole temperature range up to 550, where your magnetization is going to behave reliably. So that's my anticipation of what Richard is going to ask. So I think we are there. I don't think, I hope we've made some progress in 30 years.
Any questions?
So, if I'm understanding right, you're saying there's a positive cooling rate effect in TRM.
Yes.
Size range, so you cool for longer, over a longer period, you get a stronger overall TRM.
It doesn't have to be stronger. It could be smaller. There's a stronger, absolutely. So this cooling rate effect is completely unassociated with the traditional cooling rate effect, which is simply to that essentially you're allowing a longer period of time for magnetic particles to relax towards the field. This has nothing to do with that, really. This is a cooling rate that gives you a preference for a domain state, and that domain state is a different magnetization. It could be that at longer cooling times that the short axis or orientation is preferred, in which case you get a decrease in remanence.
But your example was...
My example, but that's just an example. It doesn't have to be that. Yeah, it could have a different effect, absolutely.
Okay, because I'm just thinking, because this has been looked at experimentally, and we only tend to see a positive cooling rate effect.
That's right, yeah.
But yeah, so given, okay, but then, even more interesting is the cooling rate effect of the PTRMs, right? Because you're saying that, you get completely different array plots based on what cooling rate you use in the lab. Would you maybe see that effect with different lab timescale cooling? So, we tend to try to reproduce results, with a slow oven and with a fast microwave. And if they agree, then, we say, well, that's more robust. And, would you expect, so that's going from, kind of tens of minutes to seconds, could you expect to see differences on that timescale?
I think, well, I think it's possible. It's hard to say what fraction of the total remanence that might contribute to. I think that's the big issue at the moment. That's exactly what Greg is doing in the project we have with Greg, looking at a much wider range of mineralogy and grain size. I think that if what you can achieve in the laboratory, though, in terms of differential cooling times is pretty small, right? Nobody's going to put in a TRM over a month. So the only experiment that's been done similar to that, I think, is Lisa's work, where she's looked at the aging of NRMs. That's basically, I interpret Lisa's work as showing that the domain states have moved over a period of aging into different types of domain states, right, which have different then stabilities.
Yeah, that was only significant for most of the samples show effect.
Well, they were all. She showed that some curved derived plots became straight, some straight derived plots became curved, and the curvature, I don't know if you say. I'm not sure that were really minor. I don't know if I honestly can't remember, to be honest, the exact variation in the gradients that she got, and then I'm not even sure if she did the gradient fits, but she showed the variation in curvature. But the question I think that is important is to what extent does this undermine reliability of paleointensities? And I don't think it does, but because we know that many of your samples do work. Right? If you get a linear OI plot That gives you that's if you get a linear right part, that gives you some indication, at least, that your samples are reliable. We have a whole set of other criteria by which you mark the stability of your grains. But there are some samples that undoubtedly will compromise that work. And they should be limited to these particles where you have a similarity of energies for different domain states. What we've seen at the present time is that occurs where you get the critical grain sizes. So the grain sizes that where you start to see vortex states emerging from single domain grains. There you have a similarity of domain states. What we've also seen an indication of, although we haven't yet pursued that rigorously, is that that's the first critical size. There'll be another critical size when you get single vortex to multi-vortex. Multi-vortex are also highly stable, and the remanence isn't so necessarily so much smaller. And of course, these critical sizes vary with mineralogy and shape. But you know, undoubtedly, this is a problem. It mirrors the problem we see already in multi-domain grains. It's not well understood, but well appreciated. Right? The multiplicity of domain states in multi-domain grains. You can never remagnetize it and get the domain walls in the same position. Same thing here, except we don't have an infinite number of locations for the domain wall, but we have a multiplicity of domain states nevertheless, which is only repeatable if you start from the same initial population of grains and domain states, and you heat it up and cool it down in the same fashion. So it's repeatable if you know what your original arrangement of the domain states were. And you can get there, probably,